So yeah, take it away, Soledad.
Thanks. Thank you so much for the invitation and for the introduction. So I'm going to talk about how one can use exact and approximate symmetries in different machine learning models. And as an introduction, well, you maybe have seen that many breakthroughs have occurred in related to machine learning and using large models. And one of the properties of these large models that can achieve interesting things is the fact that they are over-parameterized. So you may have way more parameters and data points. And so there's a question of like, how do you design the architecture so that the models not only fit your training data perfectly, but also generalize well outside the training data? And so in machine learning, there is a notion of inductive bias, which is like what are the design principles that make the models work. And there is also the notion of the double descent phenomenon that tells you that there's under some circumstances you can have over-parameterized models and perform well outside your training set as well. And so there's not a clear solution of how one can have models with a good inductive bias in general, but there's some design principles that people have observed that have worked in practice over the past 15 years. And this is the design of models that exploit the structure of the data in a way that is consistent with what the data wants to look like or looks like. And so many of these successful deep learning architectures have the properties that exploit symmetries in one or another way. So for instance, convolutional neural networks, were the ones that make this breakthrough of deep learning in image classification like 15 years ago, are equivariant with respect to translations. And recurrent neural networks, which were the state of the art for a long time in text and natural language processing, are also have some form of translation equivariance in the way that they're defined in a recurrent way. And graph neural networks are the machine learning architecture that are designed to work on graphs, and they are permutation equivariant with respect to node relabelings. And transformers, if you forget about the position encoding, they're also equivariant with respect to permutations. So there is some common pattern, which is that machine learning models that have been successful in the past 15 years have some form of symmetries in their design. And the claim is that exploiting the symmetries and exploiting other forms of mathematical structures that may occur in your data, such as geometric structures like manifolds, graphs, symmetries, etc. This is something that could be something useful for machine learning. And there's an entire area of research, which is called geometric deep learning, that studies how one can exploit these mathematical structures in the definition of deep learning models. And in your case, just structure, like using the physics structure of your problems in the design of the machine learning, instead of just using some blind model, could be more useful for your problems. And that can also be formalized in terms of like, how much do you gain in terms of generalization, error, or sample complexity by imposing the structure that you need in your models. And in the physical sciences, symmetries have other meanings as well as just inductive bias. And so as far as I know, in the physics literature, people distinguish two types of symmetries: the symmetries that are called active symmetries, that are the symmetries of physical law. So say, for instance, a system has conservation of energy, and that translates into a time translation symmetry due to Noether's theorem. Symmetries that physical law satisfy under given assumptions. And there are other symmetries which are much more rich than the passive symmetries, which are called the active, the opposite. Like the most rich symmetries are the passive symmetries, which are symmetries that have to do with the fact that when you have a physical object and you write it as a mathematical object, the choice from going to the real world to the math is not unique. There are many choices that you make. For instance, you have to choose a coordinate system, you have to choose a unit system, etc. And since that choice is not unique, if you make a different choice, so if you change your coordinate system, then your predictions should change accordingly to the coordinate system, and that can be formalized as a symmetry as well, like gauge symmetries and coordinate symmetries and units, equivariances, etc. And so we claim that writing machine learning models and data science models, when we do that, we have to impose the symmetries that the problem have, the active symmetries and the passive symmetries, and that would lead to more correct machine learning models, and these models will have better performance. That's a claim. So mathematically, we write this in terms of invariances or equivariances. So basically, the idea is that we have a data set, X, and we have a group acting on that data set. And so we say that a function is invariant if for every data point and group element, if we do a group transformation to that element, the output of the function doesn't change. So for example, I have this image classification problem, and my group is, say, rotations by 90, 180, etc. degrees, like discrete rotations. So if I apply a rotation to my input image, the classification value doesn't change. That's an invariant function. We can also think of equivariant functions. So for instance, in this example here, I have this pendulum, double pendulum with springs example. And so this has a symmetry, which is like if I rotate my masses and my velocities by a rotation that fixes the z direction, then the positions and the velocities along the orbit of this dynamical system are also rotated. So that's an equivariance. So basically, if I apply a group action to my input elements, then the prediction function is also applied the group action as well. Mathematically, one typically writes a commutative diagram that has this form, which tells you that computing a prediction and then applying a group action is the same as applying the group action and then predicting the group action, the prediction on the transform element. And so here in this commutative diagram, I say, well, actually, the action that I use in the input space may not be necessarily the same as the action that I use in the output space, but it's by the same element. So maybe in this case, there are different representations of the same group. And I'm going to have an example of like some cases where you want to have different representations of the same group. And so in equivariant machine learning, what people do typically, I mean, there are many things, but one thing that people do is they parameterize the space of functions so that for any possible parameter, the corresponding function satisfies the symmetries. So they're doing the optimization in the space of functions that satisfy the symmetries. And that is, you have to parameterize the space of functions that satisfy the symmetries, and they do the optimization in the parameters of the space. This is not the only way to do it, but that is maybe approximate symmetries, or there's other ways, but that's what we propose. And so, for example, a typical example where symmetries are very important is in graph learning. So the idea is the following. So in graph learning or in graph neural networks, people consider graphs. So here my graph, I represent it in this form. And so the graphs are given by an adjacency matrix that says what nodes are connected to what, and then node features. So each node here has a color, for instance. And so I can write the same graph with different adjacency matrix. So this adjacency matrix represents this graph, but if I permute these rows and these columns, it's just saying I'm doing the same, different order for the same graph. These two matrices represent the same object, the same graph. So then you can think of it as this is a passive symmetry. These two things, these two matrices represent the same graph. So writing G as AX, adjacency node features, is the same as writing pi G, represents the same object, which is apply the action by this permutation group by conjugation in the adjacency matrix and by multiplication of the node features, right? So these two things represent the same graph. So when I'm learning a function on graphs, say I'm learning what is the length of the shortest path that visits every node, or what is the order of this shortest path, what nodes I visit after another one, both functions will have this symmetry. So typically what people do is they learn an embedding for every node in a d-dimensional space. So you take your input, which is the graph written as adjacency matrix and node features, and then I apply permutation to the. If I apply a permutation to the adjacency matrix and to the node features, the embedding that you learn has changed as well. So permuting rows and columns here correspond to permuting the embedding that you learn. And that is an example where you act by the same group, but the representations in the input space and the output space are different, right? So in graphical networks, there are many open questions. So for instance, how can we parameterize the space of functions that satisfy the symmetries efficiently? And how can we do optimization in this space? And a lot of these questions have math-related problems. For instance, being able to distinguish different graphs is equivalent to solving the graph isomorphism problem, which is a very well-studied problem in theoretical computer science. So that leads to the fact that a lot of graphical networks architectures are not expressive in the sense that they cannot express they cannot express all the invariant functions, but they can express many invariant functions. And that brings interesting mathematical problems in this space. Anyway, any questions so far? Comments? So my idea for this talk is to give an overview of different ideas that show up in the landscape of machine learning with symmetries. So in particular, I'm going to explain how we can use invariant theory to parameterize invariant functions and equivariant functions on point clouds, symmetries with respect to the orthogonal group, and rotations and Lorentz, also units. And then I'm going to tell you about an application to contrastive learning. And then I'm going to talk about some application to cosmology and some things related to graphical networks if I have time. That's basically the agenda for the talk. So as I said before, how are symmetries implemented? So there's the exact symmetries that are implemented using techniques from either representation theory, group convolutions, or invariant theory. I'm going to explain how we can use weight sharing, which is basically what people do in graphical networks. And invariant theory, I'm not going to get into the representation theory, but you have experts like Tess that works in implementing equivariant machine learning using representation theory. And also in practice, people also implement symmetries using approximate symmetries, not exact symmetries. And for that, one of the typical techniques is data augmentation, which basically is like you generate extra training examples and the corresponding labels using the transformation that you would expect. And also using the connection between the conservation laws and the symmetries and how the symmetries can be generated in certain spaces by defining loss function penalties that can be used as regularization as a proxy for the symmetries that you want to implement. So I'm just going to start with a simple physics example of how you can implement invariant functions on point clouds. And this idea, I'm going to say it for the orthogonal group, but similar ideas will happen for other simple Lie groups where you know what the invariants of your group are using classical results from classical invariant theory. So the idea is the following. So say that I have this point cloud over here. Every point has a positional velocity. and I'm trying to predict the energy of this point cloud using machine learning. So how can I implement the functions that satisfy this symmetry? So first of all, what is a symmetry? So say I have a function that takes n vectors in Rd, the point cloud, and predicts just a scalar value, which is the energy, right? So this function satisfies that if I apply an orthogonal transformation to each of my input vectors, the output doesn't change, it's invariant. So the first fundamental theorem for invariant theory that you can find in the classical invariant theory book by Villar from 1946 tells you that the invariant functions, the OD invariant functions, are given by functions of the inner products of the input vectors. That is a complete characterization of all the invariant functions. So any function that is invariant is a function of the inner products, and every function of the inner products is invariant. So the second part is easier to see because if you have a point cloud and you rotate or reflect everything, the prediction, the inner products don't change. Yes. So for simple Lie groups, you have a different, maybe a different form, a different function here. For example, maybe I can show you my next slide. So for instance, if you're looking at Lorentz group, instead of considering the inner products, you consider the Minkowski inner products that take the temporal components minus the inner product of the spatial components. If you're looking at the special orthogonal group, you have to look at the inner products and the d by d subdeterminants of the matrix of points. Yeah, so basically you look at what are the generators of the algebra of invariant polynomials, and then you can do that. You can say that every function can be every invariant function can be approximated by those. One in what sense? Because here you also you have a set of invariants, right? So here you have all the inner products, but also all the d by d subdeterminants.
Oh yeah, sorry, thanks.
Yeah. Mm-hmm. So this is like many functions. Yeah. Mm-hmm. Okay, good. So then you can write the invariant functions from these invariant features. So you take the n vectors in Rd, you construct the invariant features, the n by n matrix of inner products, and then you can, any function that is invariant, you can just write it in terms of these features. And then what simplifies here is that you don't have to parameterize, like this f tilde can be n. So that makes it easier in some way. You can also do similar things to the symplectic group and to the unitary group. Okay, great. So this gives you the invariant functions. We can use these ideas to extend this to the equivariant functions. So the idea is that now, instead of predicting an invariant thing, I'm going to predict an equivariant function. And I'm taking this point cloud and say I'm predicting the position or the momentum or something of the one of the particles or the center of mass on here. If I want to do it for every particle, then I would need to learn n functions of this form, but they can be learned independently, right? So equivariant functions takes n vectors in Rd and then output a vector in Rd. So these are equivariant. So if I rotate or apply an orthogonal transformation to each of my input vectors, then the output is transformed in the same way. So what you can prove using ideas from what I showed you before is that a function that takes n vectors in Rd and outputs a vector in Rd is OD equivariant if and only if you can write it as a function, as a linear combination of your input vectors, where the coefficient functions are scalar invariant functions, so function of the inner products. This is true for OD, but for the other groups, you may have a different formulation, but you can use these ideas from, yeah. If you want, let's see how much time do I have. I can write a short proof of this, or maybe I can do it in the end if people are interested. Okay. But the idea basically is that one can exploit the knowledge of invariant functions to produce the equivariant functions using the fact that one can construct an invariant function from the equivariant functions in a simple way. But okay, so maybe something that I can say is that if we have a group that acts in a space, in two spaces, if I have a group that acts in B and W, then there is a natural extension of the action to the maps of the group of the maps from B to W, and then the equivariant functions between B and W are going to be invariant functions. Are going to be invariant in the space of maps. So then you can use some things that allows you to say, well, if a map, like if I understand all the invariants, then I can understand all the equivariant functions using some mathematical reduction. Yeah. Okay, so I'm going to show you a simple example of how you have a question? Yes.
Oh, yeah. Oh, thanks. Are there can you do this for most groups, or are there particular groups where you can't do this sort of mapping? Or yeah, are there
from the invariance to the equivariance?
Yeah.
Or, so if I know if I have a complete characterization of the invariance, and if I have a complete characterization of the invariance on copies of the space, then I can construct the equivariant functions. Yes, using basically the fact that you can do the gradient. You can think as the gradient of an invariant function is an equivariant function. So say if you have,
Yeah.
So maybe I can say here that if you have a function that goes from RD to the N times RD to R, and if this is invariant, then the derivative of f with respect to the last guy, so let's call this Bn plus 1. This is a function that goes from RD, and this is a linear invariant function. So if this is linear, then this is going to be a function that goes from RD to the N to R, and this is going to be equivariant. I can go into the details later.
Yeah, I think that makes sense.
Yeah.
Thanks.
So very nice. I think in particular, this discussion together with what you had a couple slides ago, talking about the representation theory approach versus the invariant theory approach. So you're emphasizing the generality of this invariant theory approach, but from the point of view of the learnability, if you do the representation theory stuff and you do the weight sharing versus learning neural networks, I mean, we're going to go there eventually, that do this invariant theory, is one intrinsically more learnable than the other, or?
So I'm not 100% sure. Something that could hurt you here is that these things are polynomials of degree 2 on your inputs, whereas when you use the representation theory approach, then you have just linear in each layer. So maybe the learnability with the linear case is easier. I've been trying to benchmark different approaches and trying to see if one is better than the other one, but I don't have any results yet, so I am not 100% sure the answer to that question, but I'd be very interested in seeing that.
Okay, no, that's great. And it seems to me that there's a theoretical advantage here, just in the sense that there's these if and only if level theorems, and it doesn't require any complicated weight sharing compared to some of the other things out there.
Yes, but to be honest, there's some disadvantage here. For instance, in the case of the SO2, you can SO3, you can look at the Wigner matrices, you can write the representations, and they're very simple. But here, if you're going to use the invariants, you have all these subdeterminants, which are very annoying to work with, and they are degree D. Well, in 3, it's not too bad, but if you want to do OD, I guess that the representation theory becomes harder as well, right? So, yeah, you have all these subdeterminants, which may be annoying for implementing the model. Yeah.
Thank you.
But also, I'm happy with OD. I mean, but I know that people like SOD better. So yeah.
Yeah, my question is, I guess, about SOD, but
Mhm.
so I guess I can kind of see the sketch of the proof
Mhm.
here. But it seems to really rely on the fact that like the theorem is like, oh, I can express an invariant function in terms of like inner products, but in SOD you have this like determinant thing. So can you so what is like the I guess analog of this proposition for like RD to the N to like RD for like SOD instead of OD? That makes sense.
I mean, if you want to do SOD, then you like using the invariants, then you have to add the determinants, and that's
Is
yeah.
the condition like a bit more complicated then because you
Yeah,
have the
it's
determinant?
more
Okay.
complicated. Yes.
Okay.
Yeah.
Cool.
Actually, and if you do SOD, then you have to add the generalized cross products. So the cross
see.
products are SOD equivariant, but they are not OD equivariant. And that's why you have very nice parametrization here. But then if I mean, I wrote it down, but I don't have it in the slide, that here you would need to add the cross products with respect to
I see. Okay.
Yeah.
Got it. Cool.
So actually, it seems like you want to see the proof, so I'm going to write it down just for simplicity. So the idea is that if you have a function from RD to the N and to RD, which is equivariant, then you can write a function that goes from RD to the N times R, D to R, which is invariant. And then with this, I mean OD. And so this function would be defined as the following: H of B1, Bn, B star is equal to the inner product between F of B1, Bn and B star. This is invariant. So this B star actually plays the role of the dual of this space. But since we are using orthogonal representations, the dual is the same as the space. And so this is invariant. So you can write it as a function of the inner product. So this is going to be some function of the Bi's, Bj's, and the Bs, B stars, right? And so since this is just a degree 1 polynomial in B star, if I take the derivative with respect to B star, it doesn't depend on B star anymore. So as a function of B star, this needs to be linear. So then this is going to be a sum from S equals 1 to N of some other functions, I don't know, let's call it G's, of Bi, Bj's times Bs, B star. And so when I take the derivative with respect to B star, here, all these cancel out, and I get the formulation that I had before. And this is something that I did for the orthogonal group. But if you do it for other things, then here you will need to use what is the characterization of all the invariant functions. So then the determinants will show up, and then you have to do the computation with the determinants and see what shows up here. And the cross products will show up. But that's basically the idea. And this can be written in general, just replacing now here, instead of you go from B to W. And so then in the other transformation, in the other setting, you go from B times W star to R, or whatever base space you have. That's the idea. Okay, so I'm going to show you a very short experiment, and then I'm going to show you some other cool use of this in contrastive learning. But I'm going to try to make it a little quick. So the idea in this example, we had the double pendulum that I had in the beginning, and this is this is O2 equivariant dynamics. But if I add the gravity as an input vector, then it becomes an O3 equivariant dynamics. And you can think of it as a passive symmetry that is like doing a coordinate transformation of the entire system. And so I can think of it as, if I want to learn the dynamics of this pendulum, I can say these are the position and momentum of the first mass, position and momentum of the second mass, and the gravity as an input. And I want to predict the position and momentum of each of these masses after a certain amount of time. And this is an O3 equivariant function. So I can write it in terms of the inner products, right? And so I can do this learning via a neural ODE. Basically, the idea is I say, well, this model will satisfy some differential equation that I'm going to parameterize as a f theta, and this f theta is going to be an O3 equivariant function of my inputs. And so this is going to be written in, like, I take my inputs, I compute the scalar products, and then I learn functions f1 through fn. And then my output is going to be a linear combination of these objects. Does that make sense? That is going to be an equivariant function. Then this is what which parameterizes the differential equation. And then I'm going to use a differential equation integrator to make my predictions, compare the predictions with the actual data that I have, and take gradient steps with respect to the parameters that define the differential equation. So that's the one way you can do it. Another way you can do it is using a Hamiltonian neural network, which basically also uses the fact that the system that I had earlier is a Hamiltonian system. So the potential energy plus the kinetic energy is conserved. So instead of learning any differential equation, I'm going to learn a Hamiltonian, which is a scalar, and I'm going to use a symplectic integrator to integrate the dynamics. And then with that, just learn one Hamiltonian function, which is basically a function of the inner products of my input vectors, and then use a Hamiltonian integrator, do the predictions, and then take gradient steps with respect to the parameters that define the model. And with that, we can show that the more symmetries that you impose, the better performance you have, which makes sense because the actual target is invariant or equivariant. And so these results over here are from a paper by Finzi and collaborators in 2021, and we just added the scalar models here. And we show that, okay, the neural ODE performs a little worse than the Hamiltonian neural network because the Hamiltonian neural network also imposes more symmetries, which is the Hamiltonian symmetry. And these are different subgroups of O3 that you can implement. And the smallest symmetry group, or the less symmetries you impose, the worse it performs, which is expected. Okay. So that's like a simple example. An extra step that you can do is to use another symmetry that we haven't used before, which is the unit symmetry. So the Hamiltonian has units of energy, kilogram meter squared divided by second square. So what I can do is I can learn it in an equivariant way, in the sense that if I take every mass and multiply it by 5, then the prediction should multiply by 5 as well. If everything that had units that was relevant to my model was also part of the model, right? So the gravity needed to be there, otherwise I wouldn't be able to do that. Also, the length of the spring and the constant of the spring, all these things have units. So in order to make these units equivariant, I need to have all these like inputs that have units part of my model. If I don't, then the equivariance is not there, right? But that's an interesting experiment to do. And the way you can impose this symmetry, which is a symmetry with respect to rescaling, which is a non-compact group and brings a lot of things. You have a kind of worm that you may want to open if you want to do the math, and Hannah knows about that. Is that if you take one approach that you can do is you can take your inputs and each feature has units, and then you can use the classical dimensional analysis to find dimensionless features, which can be constructed by multiplying and dividing things so that the units cancel out, basically. This is based on classical dimensional analysis, like the Buckingham Pi theorem, that tells you that any function that is units equivariant can be written a function of the dimensionless features that gives you a dimensionless output. And then there's a fixed scaling that gives you the dimensional output with the units consistent to the things that you wanna learn. Yes.
Is this approach sort of very similar or the same as if you were to just canonicalize in the sense
Yes.
of, okay.
Yeah. And also you can see it as a particular case of being at the invariance. If you take a gradient of an invariant function, you get an equivariant function, because this multiplication by this fixed scaling, you can think of it as taking the gradient with respect to something. Like, yeah, like if you take the gradient of a constant, you get a linear map. Yeah. But also the canonicalization, yeah, is like taking one representative of over your orbit, and the representative that you choose over your orbit is the one that is dimensionless.
Yeah.
Good. Thanks. Okay. That's just an aside. And then I'm going to show you a different application by someone else, maybe in this room, Sharut, I don't know. Sharut, she's a student of Stephanie Gekelka in CS. And basically, she led this project, which was to use these ideas of equivariant, how to use the invariance and equivariance functions parameterized from the invariance to do an implementation of contrastive learning that is equivariant with respect to augmentations. And if you're familiar with contrastive learning, the idea is the following. So you have some images. So here we are considering images of cats and dogs, and you wanna find a representation of these images in some embedding space. So here my images are going to be a space X. I don't care exactly what. And I'm going to embed them in the sphere. Just I'm going to find a representation in the sphere in dimension 128, say. And I'm just gonna find a vector and then normalize it so that it's in the sphere. And so the way typically people do this representation learning using contrastive learning is they have positive pairs and negative pairs, and they want that the positive pairs get embedded in the same points in the embedding space, and the negative pairs get embedded in separate points in this embedding space. And so the positive pairs are constructed via augmentations. Augmentations of images are, for instance, transformations that change a little bit the image, but it doesn't change the fundamental content of it. So for instance, you have this cat and you make it a little bit more yellow. You do some blurring, you do some jittering, color jittering, you do some transformations in the images. And there's like a standard set of augmentations that people use in computer vision for self-supervised learning. And so the idea that the classical Sinclair approach is to make it invariant with respect to these augmentations. And they have this loss function that implements these contrastive loss. And so what Sharut's and collaborators' idea was instead of making it invariant with respect to these augmentations, we can try to make it equivariant with respect to these augmentations. So the idea is that I want that for each augmentation that we have here, we can find an orthogonal transformation that applying the embedding and then this transformation is the same as applying the augmentation and then the embedding. We want the diagram to commute as well. So the embedding of the augmented version of X is this transformation of the embedding of X. So this should be for any for a fixed augmentation. This is fixed. So if you do it to this dog, then the same thing would happen. Okay, so how do you do that? So how do you make this representation learning equivariant with respect to these augmentations? And an interesting fact about this is that the augmentations do not typically form a group, right? Because there's so much yellow that you can make an image. Right? You cannot compose this infinitely. But these transformations over here do form a group. So this is going to be approximate for sure. It's not going to be an exact equivariance because these guys do not form a group. And so this is how you can see the power of this invariance be used in this specific case. So the idea is that you have a function that if you have a pair of points, if you have two pairs of points in the sphere, you know that the first pair of points have the same inner product as the second pair of points, if and only if there exists an orthogonal transformation that sends the first point of here to the first point of here and the second point of here to the second point of here. Right. And so you can use that to define a loss function that is going to be 0 if and only if this is equivariant with respect to orthogonal transformations. So now x prime or x prime is my dog and x is my cat. And so I say that the embedding for the augmented version of x inner product with the embedding of the augmented version of x prime needs to be, the inner product needs to be equal to the inner product of the embedding of x and the embedding of x prime. So if you have that this holds for all pairs of points, then you can show that there exists an orthogonal transformation so that applying the augmentation to my point x and then finding the embedding is the same as applying my orthogonal transformation in the sphere to the embedding of x. This can look like a little bit convoluted, but basically this is just saying that if your embedding preserves inner products with respect to these augmentations, then the embedding is going to be equivariant with respect to the augmentations. Yes.
Mm-hmm. I guess because it's approximate, I guess like, is there motivation for trying to make this equivariant? Like, do you expect a better like embedding or something like that?
Yeah, and so you get control on, I mean, this is something that people want to do a lot in the disentangled representations area of research. The idea is that there is a way to modify your object in the embedding space that gives you a predictable way of transforming the original image. So I know that if I have the embedding here and then I rotate it a little bit in this direction, then the original image will become more yellow or will become more blurry or will become more whatever. So just having that kind of interpretability in the embedding is something that people like to have for several applications. So for instance, you can use these embeddings for generative modeling, and this is something that people want to have control on, like the generative model. Like say if you have this generative model that produces the image of a face, and then you move in this direction, the latent variable, then the person starts smiling or get glasses or something like that. So this is why people want to have these kind of controls in the latent space. Yeah, great question. Yeah. So basically, the idea is that you want that augmentations in the original space of images correspond to orthogonal transformations in the embedding space. And the way Charut and her collaborators implemented this was by taking the original Sinclair objective that has an invariant term, a uniform term, and add an extra equivariant term, which is defined in terms of the expected value of the inner products of the augmented objects and the inner products of the embeddings of the original objects. So this is nice because you can do it in terms of pairs of objects as people use to, that's the contrastive learning, right? But if you wanted to do with respect to SOD, then you will need to add a lot of things that you don't want to do, right? So the fact that you can do this for this group is because the embeddings are generated by functions of pairs of objects. You could do the same thing for the Lorentz group, for instance, and the Lorentz group, you would change this inner product here, but the Minkowski inner product, and that would give you isometries in hyperbolic space, for instance. So something interesting is that, like, if you can make this equivariant loss equal to 0, then it means that you have, I mean, mathematically, it will mean that you have a group homomorphism between whatever part of A doesn't get killed to the identity and an OD. So in particular, whatever part of A that doesn't go to the identity needs to be a subgroup of OD. Well, interesting. And also we have some experiments where we do like we actually, because the theory doesn't really give you control of what the orthogonal transformation that you get is. So in particular, it could be the identity. Nothing in the theory prevents it from being the identity. But experimentally, we observe that we do not find the identity, because if we take your flowers and you make them more yellow, and then you look at the nearest neighbors in the embedding space, we do observe that they are more yellow. So we observe some form of equivariant, and we actually can reconstruct from the trained model, we can reconstruct what the orthogonal transformation that you learn for each augmentation is, though we don't have, for now, we don't have control of it. If we want it to be that, then the loss as it's defined, it doesn't tell you what it would be. And also, we can see that for some downstream tasks, having this embedding where you have this interpretability can actually help. Okay, so I'm gonna say one more thing, and then I'm gonna skip the last part. So one more thing that I can say is adding, we looked at the orthogonal symmetry so far, but in some problems, in addition to the orthogonal symmetry, you have a permutation symmetry. And so, for instance, this is some work by Kate Story-Fisher in her PhD thesis, which was advised by David Hogg. And so basically what she wanted to do was she wanted to use this, well, she wanted to do some inference in point clouds that come from cosmology. So she considered a dark matter only simulation and some point clouds that come from it, and more expensive hydrodynamic simulations and point clouds that come from it. And she wanted to learn how to go from the properties in the more cheaper simulation to the properties of the more expensive simulation. And so the properties that she was looking at were scalar properties, so invariant functions on point clouds. Invariant with respect to permutations of the points, because the order of the points is not relevant, and also orthogonal transformation, so rotations and reflections. And so we can just, to put it in the context of the math that we are looking at here, we can say, well, my point cloud X is given by n points in dimension D, so like that. And so you can have the action of OD on this side, and the action of SN on the other side. Or the OD basically rotates the points, and the SN permutes the points. And so using what we know from the beginning of the talk, we know that the OD part of the symmetry can be canceled out by looking at the inner products, right? So if a function is OD invariant, if and only if it's a function of the gram matrix. And then when you write the gram matrix, then the permutation symmetry now becomes the action of permutations by conjugation, which is the same as the symmetry of the graph neural network, right? So in point clouds, basically this OD symmetry and SN symmetry can be seen as the symmetry of graph neural networks on the inner products of the point clouds. However, this is nice, and you can use GNNs in this space, but in practice, it's not going to be so useful for Kate's problem, because you go from like many points, a million points in dimension 3 or dimension 6 to a million points, a million by million matrices, which makes the space much larger and not so useful to work with. So there's some work where we can use some mathematical tricks to write the invariant functions with respect to this group action using Galois theory, which basically comes to this. When we write the the matrix of inner products, and then we look at the action of permutations in this matrix of inner products. Any permutation can, the permutations can move diagonal elements of this matrix to diagonal elements of this matrix, and off-diagonal elements to off-diagonal elements. So you kind of have two orbits, but you cannot do these two changes independently. So there's some like thing that has to glue how to permute off diagonals with diagonals. And so you can think of it as you have a Sn is a subgroup of the group that moves diagonal to diagonals and off diagonals to off diagonals. For this group, finding the invariant functions is not too hard. It's actually pretty easy. You can do it using deep sets, if you know what that is. And then you can use Galois theory to go from like the field of invariant functions from here to the field of invariant functions for the original action that you care about. And this is basically adding some extra function to the space of functions that you were considering. And then there is another trick that we use to, instead of computing all these objects, we use something that is lower rank. But I'm not going to go into the details, but just saying that that's something that that can be done. And I know that I'm almost out of time, so I'm going to skip the things about message passing neural networks, but you can think that, well, graph neural networks also have this symmetry that I showed you earlier, so it makes sense to see it in this context as well. I'm just going to go to the end. I'm going to say approximate symmetries, I believe, and this is something that maybe we can go into the math, give you a good inductive bias for machine learning problems. In the physical sciences, we have this problem from cosmology. I can give you more details about that if you're interested. We also show you how you can use this for engineering applications like contrastive learning, how you can define better representations of images using these symmetries. And something that I didn't get to talk about is you can think of the rows of symmetries as small selections. And there are other problems that also have symmetries like dynamical systems on vector fields, dynamics of oceans, I don't know, many interesting things that one can look at. Yeah, that's it.
Thank you, Soledad. Questions?
Thanks, Soledad. Can you go back to this example where you were doing the point cloud case, where you had endpoints in your point cloud, and step one of the invariance, if you wanted to kind of think about the ON invariance, would then go from an order n problem to an order n squared problem, which is like the objects that you're moving around. With what you have on the next slide, I didn't quite understand. Does this actually reduce the computational complexity of the problem back down to ON?
So something that you can do is, so you have this matrix of inner products here. This is n by n, but the matrix of inner products is low rank. So this is like this is a rank D n by n matrix. So something that you can do is if you, and this is also symmetric actually. So if you observe D rows at random from this matrix, then you can reconstruct the entire matrix with high probability. I mean, there exists a unique reconstruction. And so what you can do, for instance, is you can take your point cloud, take the k-mean centers for k equals to D, and then compute the inner products with respect to these k-mean centers. That is going to be equivariant because when you rotate your point cloud, the centers rotate as well. And information theoretically, with high probability, you can reconstruct the entire point cloud from that. So we use these invariants in general, but then we reduce these invariants to work with like the rank D version of this matrix. And from here, then you don't need to even compute the n by n inner products.
So it goes from an n squared to an n times d.
N times D, N times D plus something. Like you need to have more extra things just so that it's stable. Mhm.
More questions?
There's a
I've got
question
from online.
Yeah, maybe we can take the question on Zoom.
Hi, Soledad, it's Tess.
Hi.
Thanks for a wonderful talk. I always am really excited to see what you're thinking about. I had a question from fairly early on regarding using invariants to parameterize equivariant functions.
Mhm.
And I was curious as to, I suspect the answer is probably yes, but do you have an intuition for like generalizing this to equivariant functions kind of on arbitrary tensors of the representation? So for example, you describe vector fields, but could it also be pseudo vector fields and symmetric traceless fields, things like that? Do you think that there's a similar construction kind of for arbitrary tensor fields on the group?
Yes, I think it's the same construction, actually.
Yeah.
I think it's this construction over here. So
Nice.
basically, you, so say this is a tensor field and this is a tensor field or a tensor product of the original space. So then what you can do is if you find the invariance from your original tensor input times your original tensor output, maybe if your action is not orthogonal, then you need to look at the dual representation.
Yeah.
Then if you know the invariance here, and actually the ones that you care about are the invariant functions from here, this times this, that are linear with respect to the second coordinate. So actually using the techniques that you do, then you already have the linearity in the techniques that you have. Then if you take the derivative with respect to the second coordinate, then that would give you an equivariant function of the first coordinate.
I see. And it's okay for these to be like mismatched in a sense, like one's a vector field, like V is a vector field, but W is a pseudo vector field or something. Like they don't have to be the same. They can just,
So
yeah.
So then in that case, the representations are different, right?
Yes. Yes.
Yeah, but it can be different. Yeah, because, but then you will need to use the dual representation in the output space.
Okay, then maybe a quick follow-up question then is, do you think, as far as like comparing kind of the invariant parameterization versus kind of having arbitrary equivariant interactions to achieve an invariant or equivariant function, do you think it's fruitful to kind of quantify how those two function spaces scale depending on the various kind of hyperparameters you would have in the second case?
Scale in the sense of how many functions can you express?
Yeah, sorry, yeah, the scale of how the size of the function space scales.
Yes, I think that would be interesting.
Yeah.
This approach, by the way, the idea of having the invariants, you can do it in some cases where you know how the invariants look like, but some other cases, if you have like a very complicated group, so for instance, the group, even not that complicated, like even the group that we were considering here, which is a semi-direct product of OD and SN, we can construct generators for the field of invariant functions, so field generators, but we don't know how the algebra generators look like. And actually, probably the algebra generators would require an exponential size, right? Because the graph isomorphism probably we don't expect.
That's super interesting.
Right? So then, yeah, I mean, if you simply groups, you're fine. But then if you have other groups where you don't know what the invariants look like, then you may have a scenario where you don't know how to parameterize invariants, and then that will make it harder. But also the representations of this semi-direct product may not be that easy to find as well. But you may have an algorithm that actually does it.
Yeah.
And then you can do the linear maps and all that.
Yeah, no, super interesting. Thank you.
Thank you. No, thank you so much.
Here we can take,
At the risk of belaboring a point that I think you already said very clearly, but it seems very powerful and I want to use it in my research. So this equivariance from invariance is without loss of generality under reasonable assumptions, is that right?
Yes.
So there's no loss in taking this form. It's not making an assumption. It's not making any assumption at all, really.
You
Like,
make the
this is-
assumptions that you know what the invariants are, and then you can write what the invariants are.
right, but for certain groups, all of the invariants are
Yeah.
known, and therefore you can do this without loss of generality. And it
Yes.
seems there's theoretical guarantees that I simply don't see being present in the weight sharing case.
Mhm.
But is that right?
Yeah. Well, it may happen that, for instance, if you look at the invariants for the graph isomorphism problem, like the polynomial invariants, then those ones are like counting, basically counting subgraphs of a graph. Like then you need to write all the polynomials that count triangles, all the polynomials that count blah, 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 all the substructures that the graph can have. And so, sure, the invariants are known, but what is the size of this space?
And they're much more complicated, but for OD and for things like this, it's
Yeah.
much, much easier. For
Yeah.
Lorentz also, I guess.
Yeah.
Thank you.
Sorry?
Just to check, there's no like continuity assumption on the functions or anything in that result, or is there? Like the equivariance, invariant
Okay.
coefficients.
Okay. So this this construction is an algebraic construction, so it's valid for polynomials and also it's valid for smooth functions. You can have, in some cases, you can have a continuity assumption. Like if you want to parameterize all the functions that are equivariant with the Lorentz group, for instance, you know that there's this like light cones in the Lorentz group. And so you could define a function that is equivariant, that is defined as one thing in the complement of the line cones, and that's a completely different thing that has nothing to do in the light cones. And that would be equivariant just because these light cones are fixed. And so that would not be continuous or anything like that. So maybe this formulation would not exactly work because you have that discontinuity. But if you restrict to things that are continuous, that approximate, you can approximate it by polynomials, then that would work. Because this construction that we have here is comes from algebra. So it's basically based on polynomials. So great point, Hannah. Yeah. Thank you for.
All right, with that, let's thank Soledad again.
Mhm.